Today's lesson is for linearization and differentials. So since there are two objectives, I wanted to make sure we have time to cover both of them. That's why I'm going to have you watch this video. So please, in your warm-up books, you should be finding the equation of the tangent line to the square root of 1 plus x at x equals 0. This is old news, right? Find the equation of a tangent line. Right? To find the equation of any tangent line, it's just in point-slope form, right? Y minus blank equals blank parentheses x minus blank. But I want you to think about this, right? Where we put the x-coordinate here, x sub 0, and the y-coordinate here, and we put the slope here. But I want to do a little bit of rearranging of this. Firstly, I want to call y f of x. And then since I want f of x to be by itself, I'm going to add the y component over here. So I'm going to say, I'm going to write the slope, I'm going to add this here. So I'm going to have the y-coordinate, y sub 0, right? Just add it to both sides, plus the slope. But remember, the slope we get, what is the D word for slope? And the slope is f prime at an x, parentheses x minus the original x. So I want to use this equation, and I want to use the equation in this form to write the equation of the tangent line to the square root of 1 plus x, which of course we can also think about like this, right? 1 plus x to the 1/2. So the first thing we do is find the derivative. So f prime of x is 1 over 2 times the square root of 1 plus x times the derivative of the inside, which is just 1, right? Chain rule. So that's my derivative. Now what is my derivative at 0? One-half. So the equation of the tangent line is f of x is equal to 1/2 x minus 0, right? This is x sub 0. What is the y-coordinate? I know what f prime of 0 is, but what is f of 0? F of 0 is just 1 plus 0, right? Which is 1. So there's the equation of the tangent line. Now, use the tangent line to approximate y of 0.05. Now remember, the whole deal of this is we learned way back in Unit 3A that a tangent line, right, a tangent line is supposed to approximate the curve. So here is the square root of x plus 1. At 0, where x is equal to 0, y is 1, and the slope of the tangent line there and the slope of the curve is 1/2. But the whole idea of the tangent line just brushing by the curve is that around the point of tangency, which is 0, if you go a small distance to the right or a small distance to the left and plug in these values to the red tangent line, your tangent line values will be not exactly the blue curve values, but they'll be close. But if you use a point way out here, look at how far away the tangent line is from the curve as x gets too far from point of tangency. Then the tangent line is no good as an approximator. But as long as 0.05 is close to my point of tangency, I can use the tangent line to get a good approximation. I know this sounds silly because why wouldn't you just plug it into the square root of 1 plus x? But we're using easy functions to get at a deeper concept. So let's just follow the directions. Use the equation of the tangent line. So f of not 0, but f of 0.05 is equal to 1 plus 1/2 times 0.05. Right, and using a calculator, if you wish. And I do want you to get out your calculator. We are going to be using it. Is this what I want? Yeah. I want you to notice that what I put into y equals, into y1 I put the square root of 1 plus x, and then y2 I put a half x plus 1, the equation of the tangent line. And I've graphed both of them. And if I hit trace 0, both functions are 1. Notice this is y1, and if I go up to y2, right, the tangent line at 0 is also 1. But the minute I move away from 0 on the tangent line, you can hopefully see that the tangent line values are above the actual function value. Right? They're above, but they're close as long as I stay relatively close to the curve. So what is, if I hit trace and I want to be on y2, and if I put 0.05, the y value is 1.025. This value, right, f of 0.05. Oh, you know what? You know what's a dagger? The dagger is that if I keep calling the tangent line f, how can I differentiate the tangent line from the original? Well, I know I've called this y, but what if if I call this f of x, it's confusing to call the tangent line f of x as well. Let's fix that. Instead of calling the equation of the tangent line f of x to differentiate, pun intended, from the original function, how about we call this capital L of x for the line of tangency, or the linearization of the original function. So instead of plugging 0.05 into the original, we're plugging it into the tangent line, and using L should make that more obvious. So if L of 0.05 is 1.025, I wonder what the actual function is at 0.05. What is into y1, put 0.05. Gee, I get 1.024 blah 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 blah. Pretty close though, right? 1.0246. Matter of fact, if you cut that off, do AP rounding, right? 1.0246 would be 1.025. These two values are really close. Using the tangent line, using the original. That's the focus of today's lesson, part of today's lesson. Linearization. Find the linearization of a function at a point and compute differentials. So this little word at the end seems like it, hardly notice it. We really are learning about objective 1 is linearization, and objective 2 is differentials. I've really taught you about linearization already. So again, just another drawing for any function f of x. Its tangent line is a close approximation of the function as long as you are a small distance from the point of tangency. So if I have x equals some point of tangency, x coordinate of tangency, y coordinate of tangency, the function and the tangent line share one point. The point of tangency is the same on both the function and the linearization of the function. Because remember, the whole idea of local linearity was that as long as you are a close distance around the point of tangency, if you zoom in here, the curve appears to behave like its linearization, like its tangent line. So we can call the equation of the tangent line the linearization of the function. You cannot imagine how much mathematical calisthenics engineers do with crazy functions to make them linear. They linearize them on little teeny intervals. If the curve is crazy enough, it'll linearize it on a small domain, and then different linearization on a different piece of the domain, and because even computers are faster at processing linear values versus nonlinear values. I mean, computers are faster than us at anything, but they can compute so much faster than we can, but they still increase a computer speed if you are using lines instead of nonlinear functions. So if you are asked what is the linearization of a function, you need to say to yourself, that's just a fancy way of being asked for the, whoops, I don't want that. The linearization of f of x is just asking for the tangent line equation. At x equals a is the x coordinate of tangency. So what's the information I need? I need the x coordinate of tangency, the y coordinate of tangency, and the slope at the point of tangency. Those are the things I need to write the equation of a line. So here again, as I did in the warm-up, point slope form of a line is y minus the y coordinate is equal to the slope times x minus the x coordinate. Just rearranging that, add f of a, move the minus f of a to the other side, it becomes positive. Slope, right? Pull this out at parties, it looks so fancy. It's so impressive, I'm so smart. It's really just algebra 1. And in books, the standard linear approximation is just point slope form, where they replace y with L of x for the linearization, or the linear approximator, as long as you are close to the point of tangency. So this is the point, x-coordinate of the point of tangency, and what you're going to put in here, these are values close to the x-coordinate of the point of tangency. For an x close to the x-coordinate of point of tangency, you have the function itself is very, very close to its line, right? Function behaves like its tangent line. This is just a tangent line approximator. In the dreaded Unit 9, we call this the first order approximation because lines, right, are an x to the first. That's called foreshadowing. So here is our warm-up, the picture that I showed you on the calculator. And then I want you to look at these values. F of 0 was 1, because that's the point of tangency, and the line was, the linearization, the tangent line, at x equals 0 was also 1, right? That's this point. 0, 1. So the difference between the function and its approximator, the tangent line, is nothing. The error is nothing. But what about 0.05? Right? What is the value of the function at 0.05 versus the linearization at 0.05? I'll show you a way I'm going to look at the calculator to capture these values a little bit better, a little easier. Right? I have both of those functions into y1, and then in my calculator I set it up to darken the ask so that when I go over here to second table I can put in 0 and see, of course, that they are both the same. Then I can put in 0.05 and 0.005 and 1 and 2. I could also then, in y3, enter y1 minus y2. And there you can see how small the error is, right? The function value minus the linearization is exact at the point of tangency. That number is -3 times 10 to the -4th, right? -3 times 10 to the -6, super small, -0.08-ish, -0.26-ish. So you hopefully see that the error is getting bigger the farther I get away from the point of tangency. Right? When I'm here at 2, I can see the space. Right? I can see the space here. There's my error. It's red. See that? But over here at 1, I can barely see the difference between the line and the curve. Over here at 0.05, I cannot tell the difference at all between the two. And that's why there is a very small difference. That error was, right, -3 times 10 to the -4. So some notes. I don't actually care what these values are here, but I do want you to note that the error gets greater the farther, whoops, I guess error would be over here, stupid. These values, the error gets greater the farther you are from point of tangency. Another thing to note was that the error, because the function values were always below the line. Yes, do you agree with that? The function values were always below the line. So does it surprise you that the error values were all negative? Right? Does that surprise you? And when I do say error, I do mean the absolute value of the error, right? I know that these negative values were getting more and more negative, which is technically smaller, but I'm talking about distance, absolute value, the distance of the function from the line, the curve from its tangent line. All of these values were negative because the function lied below the curve. So here are some common and important linearizations. Notice I found the linearization by taking the derivative. That's why this is in the application of derivatives. Any function of the form 1 plus x to the k, its linearization is always going to be 1 plus kx. Remember, for us it was 1 plus, what we did in the warm-up was 1 plus x to the 1/2, and the tangent line was 1 plus 1/2 of x. So what if I change this to 1/3? Right, the cube root of 1 plus x, you know what its linearization would be? 1 plus 1/3 of x. This is not worth memorizing. AP is not going to test you on these common linearizations, but they might ask you for these linearizations, and it's just nice to talk about and hopefully make sense. Does it make sense to you that at 0, this is at 0, point of tangency being 0, at 0, sine x behaves like the line x? Does that make sense? There's sine x. Does it make sense that at 0, sine behaves like y equals x? That's kind of nice to know that sine x, which is a sinusoidal curve, around 0 can be approximated by this simple line y equals x. What do you think about cosine? What do you think cosine's linearization is? Well, duh, it's the constant function 1. Does that make sense? Oops, sorry. Here is cosine x at 0, the point of tangency. Does it make sense that the constant function y is always 1? As long as I stay close around 0, that cosine x can be approximated with the function y equals 1. Crazy, right? Now I want you to look at this next one. Tangent, that certainly does not look like the function 1, does it? What does that look like? At 0, does it look like tangent is approximated by 1? No. This is a typo. What do you think the approximation of tangent x is at 0? What does it look like? How could I prove it? Well, what is the point of tangency? A equals 0. What is f of a? What is tangent at 0? 0. What is f prime at 0? What is the derivative of tangent? And what is secant squared at 0? So what is the equation of the linearization of tangent? Is f of a, which is a is again 0, 0 plus f prime of a times x minus a. And of course, that simplifies to x. Here's one of the ways to use linearization, and it doesn't even look like this is calculus at all, or a calculus question. Who said, you know, derivatives? I'm talking about the square root of 80. Huh? So the square root of 80 is not a rational number, it's irrational. Well, what if I want to get a good approximation of it? And there are some homework problems like this. Approximate the square root of 80 by using a linearization centered at an appropriate nearby number. So, if I said, what is 80 to the 1/2? I want to use a linearization of a function. 80 to the 1/2 is not a function. So do you see where I took this and imagined any x to the 1/2 so that I could create a function? Now, of all the numbers in all the world, if I choose a convenient value near 80 to plug into this function, what do you think I will pick? Yes, Alex, I think I'll use 81. Do you see why? So, how about I say, find the linearization of the function, the square root of x, at x equals 81. And then use my linearization to approximate a number close to 81. So what do I need to do? I already chose A, and this is what makes this problem kind of hard. I chose A, the book didn't give it to me. If I choose A to be 81, what is f of 81? True? Don't anybody tell me that's plus and minus 9, please. The answer is 9. 81 to the 1/2 is a 1-to-1 function. The answer is 9. Then, what is f prime at 81? Well, if f is x to the 1/2, isn't it true that the derivative is 1 over 2 root x? And that is 1 over 2 times the square root of 81. Do you see why I chose 81? Square root of 81 is 9, so this is 1 over 18. Now let me write the linearization of the square root function centered at 80 is f of a, 9, plus f prime at a, x minus a. And what am I going to plug in there? What am I trying to approximate? Side note, delta x, the change in x from 81 to 80. That's interesting. So what is this? 9 plus 1/18 times 80 minus 81 is generally -1. Right, so that is 9 minus 1/18. What is 9 minus 8.9444444? What is the square root? Excuse me, that's my phone. Square root of 80. Oh, gee, those two numbers are pretty close. Right? So you making a linearization, creating a function, making it a linearization so that I could approximate the square root of 80. And look how close I am. I'm good to write 1, 2, 3 places past the decimal. Crazy, whack, funky, eh? Alright, second objective. Objective 2, differentials. So, when we first talked about derivatives, we talked about good old rise over run. As we shrunk delta x to 0, we called them really small change in the rise compared to a really small change of the run, right? So same picture that I had before. Remember this cloud, right? As long as I stay a small delta x away from a, that f of a, which is the same for the line as it is the curve, right? At the point of tangency, they're exact, but if I go a small distance, now I'm choosing to go to the right, but I could have just as easily gone to the left. If I move from a very small distance away, when I go up to the curve, this is f of a plus a little bit, right? So imagine this is 3, and this is 3 plus 0.01. This is the function at 3 plus 0.01. That function value is below the linearization value. So here's my delta x, here is my delta y, a vertical change between f of 3 and f of 3.01. Now let me erase, whoops, sorry. Now I want you to look at what I've done. I've used the same 3.01, but instead of going just to the function value, I went to the linearization value. Right? This is the linearization at 3 plus a little bit. This right here is my error. The difference between the linearization and the function value is a vertical error. The change between f of 3 and L of 3.01 is not quite the same as the difference between f of 3 and the function at 3 plus 0.01. But the change in L, the change in the linearization from the point of tangency to a point a little bit away from the point of tangency, as long as you're close enough, delta y and delta L are close. And how far are they off? Error. This error right here. And we always want to talk about positive error, right? So, dy can be considered a small change in y. dx, a small change in x. So, if my change in y, this is the actual change in y. If the actual change in y is really close to the actual change in the tangent line, then L of 3 plus a little bit minus L of 3 is the same as, right, this tangent line. See, try to follow this algebra. Plugging 3 and a little bit into the tangent line is plugging 3 and a little bit into the tangent line. That's what it is, right? Now this throws kids sometimes, but all you have to do is remember algebra, algebra 1. If I said If I said L of x is 1 plus half x, right? What is L of 3.01? It would be 1 plus half 3.01. That's all I'm doing. I'm taking a plus dx and plugging it in for x to the equation of the tangent line. But if you notice what happens here is some nice algebra. I'm going to go ahead and erase my crap. Some nice algebra happens here. The a's go away, the f of a's go away, and all you're left with is the derivative at the point of tangency times the small change in x. And what do I get out of that again? I get the actual change in the tangent line, which is really close to the actual change in the function. I know your head's probably spinning now. That's what we call a differential. If y is a function that is differentiable, the differential dx by itself, not dy over dx, just dx, can be considered an independent variable, and the differential is dy. I want you to look at what this equation looks like if you divide both sides by dx. Right? dy dx is equal to f prime of x. Right? So here's a very straightforward question about differentials. Find the differential. Say to yourself, that means find dy with no dx underneath of it. Find the differential. Oh, somebody used a p. Oh, for God's sakes. Think of this p of t as your, right? Let's write this way. Y equals x cubed minus 2x plus 3. So evaluate dy when x is equal to 2 and the small change in x is 0.01. Okay? I mean, go ahead and use the p's if you like, but I think sometimes it's nice just to use your standard x and y's when you're first doing this. So, step 1, actually find not dy, but dy dx, right? Which is just f prime of x. You know how to do that, right? If y equals x cubed minus 2x plus 3, dy dx is 3x squared minus 2. Multiply both sides by dx. So multiply this side by dx and this side by dx. The dx's cancel out and you end up with dy, the differential of y, is equal to f prime of x times your teeny tiny change in x. Now they've given me stuff to fill in. So, oh, that didn't make much of a difference, did it? The differential of y is 3x squared minus 2 times dx. What is the x they asked me about? 2, and the dx, 0.01. So plug in 2, plug in 0.01. 2 squared is usually 4. 4 times 3 is sometimes 12. 12 minus 2 is 10. 10 times 0.01. Nope. So I'm going to erase my work and I'll show you with all the p's in it. So dp dt is 3t squared minus 2 times dt. Plug in. And what does that say? this is important. What this is actually saying, if you change x by just 0.1, then your y, if you change x by from 2 to 2.1, then your y value will change by approximately 1 unit. That's what this means. If you change x from 2 to 2.1, the y change will be approximately 1. So let me show you an application with, maybe some application where you can see this maybe a little bit better. So, if you have a circle with a radius of 10, and if the radius increases by 0.01 from 10 to 10.01, approximately how much? Approximately how much will the area change? Well, firstly, I need to understand that if I'm talking about area of a circle in terms of its radius, we have pi r squared. So, step 1, take the derivative with respect to, take the derivative of area, not with respect to x. What variable do you see here? dr, right? So remember, pi is a number, right? That's just a constant. So what is the derivative of area with respect to this variable r, right? 2, bring down the 2, times the pi, times r to the first. Let me just pause for a second here and let that sink in for a minute. Yep. The derivative of area is freaking circumference. OMG. Make it stop. Math is freaking awesome. Gee, I wonder what the derivative of volume is. But I digress. So, step 1, take the derivative. Step 2, multiply by the small change in radius. So multiply that and I get the differential in the area is 2 pi times the radius times the teeny tiny change in the radius. Remember, this is the differential, which is an approximate. The differential approximates the actual change. The differential approximates actual change, because the differential is the actual change in the tangent line. It approximates the actual change in original function. So what are they? Then step 3 is plug in. So the differential in the area is 2 pi times my radius times the teeny tiny change in the radius. Yes? Let me go ahead and go through the slide with this. Very small change in the area, very small change in the radius, and I get 2 pi. 2 pi, so 6.28-ish, is the approximate change in the area of a circle with a radius 10 if you change the radius by 0.1. Hopefully you can maybe imagine how this would work in engineering, right? If I want, there's always plus and minus, right? Every single Coke can isn't exactly the same. They want to know, I have to construct and engineer my machines to make Coke cans that are going to hold, right, the surface area and hold the volume of blah, 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 and I can have an error of just a little bit. What happens if the radius of my Coke can, instead of being, 1.5 centimeters, I don't even know if that's realistic, but 1.5 centimeters, what if my machine happens to be off a little bit and it's not exactly 1.5, it's the radius is 1.52, right? How much is that going to affect the size of the overall can or the volume of the Coke it will hold? That kind of thing is where differentials are used. So I hope, I did want to say that, of course with this we can actually, right, what is the actual, right, the actual area of a radius 10.1 we can figure out, right? Area is pi 10.1 squared. Can you compare that to the area of pi 10 squared and then find the difference? Of course you could, right? You can actually find that difference. So this, when I did my, right, let's use our, oh darn it, calculator, right? What is, right, 100 pi, oops, right, so that's the area of a circle with radius 10, but what if I have 10.1 as my radius? Gee, what are you off by? Ah! Whoops. G, 6.3-ish. We said the error would be approximately 6.28-ish, which of course rounds to 6.3. Crazy, right? So, linearization and differentials. That's what your homework is on, and I will check that homework tomorrow. Have a great rest of your day. Bye-bye.